Thank you so much for the opportunity to be here and for that kind introduction. I'm very excited to have the opportunity to speak with all of you today about my work over the last 25 years in working with asbestos. Oops, I skipped a slide. So my objectives today are to, first of all, focus on asbestos-related diseases, particularly from an immunological perspective. Most of my work has been on, as Dr. Delahaus said, on autoimmune diseases. And so I want to bring that forward, but also focusing on how the immune system participates in other outcomes of asbestos-related disease. And then I'm going to play around a little bit. Hope you have a sense of humor this morning with these mechanisms to other pulmonary exposures and their associated pneumoconioses, just to take a look at the role of the immune system in so many health outcomes. With the next few slides, I'm just kind of playing with an idea that I call a nonlinear relationship between exposure and outcome. Because so many different things happen, and yet there are so many different outcomes that can end up. What does the person end up with at the end of this exposure? So the first one is amphibole asbestos, and you can see in the upper right-hand corner, there's an electron micrograph of amphibole asbestos, which is a needle-like form of asbestos. And because of its needle-like shape, its aerodynamic diameter and its ability to travel in the laminar flow in the airways is exceedingly small, and 0.06 to 0.7 microns, so that it travels in the laminar flow quite easily with a very low Stokes number. As you can see, we have lots of things that happen: oxidative stress, signal transduction, behavioral cell changes, cell death, inflammation, cytokines. And then we start to see the actual damage that's caused by the asbestos. And then finally, we end up with a whole group of different outcomes: asbestosis, pleural fibrosis, mesothelioma, lung cancers, other cancers, and autoimmune disease. With the next slide, I'm going to take a look at chrysotile exposure and show you how different that is. So if we look at chrysotile, I'm sure you're all familiar with chrysotile. It's a little bit curly. It's in the serpentine family of mineral fibers. And because of its curly shape, it doesn't stay in the laminar flow as well. It has a larger aerodynamic diameter of about 0.1 to 1 micron. So it doesn't flow as well in the laminar flow as the amphiboles. But as you'll notice toward the top here, all of the same things happen with cell changes, and we see the same similar things happening in the tissues, but we don't get any autoantibodies and we don't get autoimmune disease. So what's going on there? If you look over to the left side of the slide, you'll see my sort of list of all of the things that are going to impact what happens in terms of that exposure in an individual. Are these differences due to fiber shape and size? And there's a lot of work going on right now looking at fiber shapes and sizes, and definitely that's going to play a role. Fiber composition is interesting just from a simple point of view. Amphibole asbestos has a tendency to be polyanionic on its surface, whereas chrysotile tends to be positively charged on its surface. So that charge difference is going to make it behave differently in the proteinaceous and cellular environment. Internal dose is an interesting concept of that's very difficult to measure. We know maybe how much was inhaled, but we don't know how much was coughed out or swallowed or other things happen to those fibers to determine what actually remains in the body and where those fibers go. What cells are affected is going to be critical. Obviously, the first cells impacted will be epithelial cells and alveolar macrophages. But then as the inflammation progresses, you'll see many, many more immune cells arriving on the scene. I'm not going to talk about genetic background today, but I acknowledge the strong influence of genetic background on health outcomes. And that's related then also to all of these other things like their immune status, their redox status. What is their overall health? Are they on medications that affect their immune system? Are they just getting over the flu when they get exposed? All these different things that are individual are also going to impact their health outcome. Let's take a look at silica. So silica has a larger aerodynamic diameter because of its chunky shape, and it's not fibrous, so 4 to 8 microns long, or excuse me, in aerodynamic diameter. Expose cells to silica and you get the same kinds of things happening. All of these same things happen, including autoantibodies. But with silica exposure, we really don't see mesothelioma. We don't see other cancers away from the lung, primarily lung cancer. We don't see much in terms of pleural fibrosis, but we do see the interstitial fibrosis in the form of silicosis. So what's the difference there? What's going on? Those are the kinds of questions that I want to talk about today. I have one more. This is beryllium. This would be a metal particle exposure. Beryllium oxide or sulfates are used in manufacturing many products. Its aerodynamic diameter, because of its sort of odd shape, is 5 to 14 microns. And again, expose cells to beryllium and you get all kinds of cellular responses, the same kinds of things. But in the end, the primary outcomes of beryllium exposure are these T-cell granulomas, and then a little bit of interstitial fibrosis and lung cancer. After the years of working with Libby since about 2001, we have come up with a whole bunch of lessons that we like to talk about that have really changed the dynamic and the paradigm of asbestos exposure. So I'd like to go through those very quickly. First of all, mesothelioma and asbestosis, the two diseases that we most often relate to asbestos exposure, are not the predominant asbestos-related diseases from amphibole exposures. We've learned that from Libby, where actually autoimmune outcomes and newly described pleural outcomes are the predominant diseases in Libby. Second, fibers that do not fit the strict definition of asbestos, and that would include Libby amphibole, which is a mixture of amphiboles, non-regulated amphiboles, nanofibers, other elongated mineral particles, EMPs. All of these things cause asbestos-related diseases, mesothelioma, asbestosis, etc., but they are not regulated. And this causes a problem for you and as clinicians and for me as a researcher in that we're dealing with materials that are causing disease that are not, we may not be notified about. For example, I was involved in a lawsuit. I don't do litigation anymore. I just can't stand it. But I was involved in a lawsuit where a family was exposed to Libby amphibole because it was in their attic. And when they had some remediation done, some of that material fell through into the house. And they were very, very concerned about this. When they sent away the material to the testing laboratory, it came back as non-detect. And that is because Libby amphibole is not regulated asbestos, and therefore they didn't count it as asbestos. So they said there's no asbestos there. So these are the kinds of problems that we have in terms of helping people with these exposures. The exposures to these non-regulated materials are increasing while chrysotile exposures are decreasing. There are a lot of controls on occupational exposures from chrysotile. And even last year, there was the supposed ban that was supposedly banning asbestos, but actually wasn't a ban at all. It was simply a restriction on some limited uses for chrysotile. Amphibole wasn't mentioned at all. Again, non-cancer health effects of amphibole exposures occur, and at very low exposure levels. We have mouse studies and some unpublished clinical reports from Libby that show that the exposure standards that we use for cancers don't really apply to these non-cancer outcomes because disease happens at extremely low levels. There are also fiber-specific outcomes. Over the decades of my work with asbestos and long before I started working on it, a lot of papers simply talked about asbestos and didn't differentiate between the amphiboles and the serpentines like chrysotile. And that made it very difficult to determine what the health outcomes were because these two types of fibers have different outcomes. And finally, very, very tiny fibers detectable only by electron microscopy, being less than 5 microns long, are not regulated. In fact, they're not even counted as asbestos according to the current detection and counting schematics used in the United States and most of the world. And so therefore, again, if you send out a tissue sample wondering if the person was exposed to asbestos and all the fibers are less than 5 microns long, it will come back a non-detect because those fibers less than 5 microns long are assumed to be non-pathogenic and are ignored. So part of what I'm going to tell you today is that I don't think they're non-pathogenic. I think they're very critical because of their impact on the immune system. This is a map that was put together last year by my colleagues Brenda Buck and Brett McLaurin for a paper that we published in Autoimmunity Reviews, looking at the public health risk for asbestos exposure and talking about the fact that asbestos is not gone. This is not a bygone era of asbestos exposures. Asbestos is in our rocks, and as urban development expands and we dig into the bedrock for road building and homes and cities, and also as climate change affects the aridity of the soils, we begin to see more dusts containing asbestos. So it's with us, and it will always be with us, and it is a current public health problem. Very quickly, I'd like to give you an introduction to the story that happened in Libby. I'm sure most of you are aware of that. This was a developing town in the early 1900s with mostly mining and timber. And then a mountain was discovered that had vermiculite in it. And that led to the town really growing a lot because of the mine and because of the processing plant that was in the town. You can see that it's very beautiful here. These are the Cabinet Mountains up in the northwestern corner of Montana. That's the Kootenai River that flows through town. And the mine is far up in the mountain to your right. And the ore was brought down into town by rail and then to the processing plant over here on the banks of the river. So this is Libby up here in the far northwestern corner of the state. And then this is where I am today in Bozeman, Montana. And we do have about 3 feet of snow on the ground. And I think that those of you in New York are very, very used to having a lot of snow around. The vermiculite was found to have really, really good insulating properties when expanded with heat. So you can see down here at the bottom, this is the ore as it comes out of the rock. It looks like mica. But when you heat it, it pops open and looks like little accordions. And that's what gives it its tremendous insulation properties. Unfortunately, when you heat it and pop it open like that, billions of little tiny asbestos fibers pop out of that ore and you breathe them in. Libby produced the vast majority of vermiculite for the US and Canada for decades until the story broke in 1999 when Andy Schneider, a reporter for the Seattle Post-Intelligencer, wrote about people dying in Libby. And that's when the EPA came in and the Superfund program started funding research on Libby amphibole. Despite the cleanup that has occurred in Libby, millions of homes and other buildings remain insulated with Libby's vermiculite in North America. And we were just talking this morning about the World Trade Center towers, and when they came down, they were insulated with monocoat spray-on insulation. So there was asbestos in those buildings. And the millions of homes in the United States remain insulated with a zonal insulation shown here. The bag is torn open in somebody's attic. That's the loose insulation used in attics. The Center for Asbestos Related Diseases started right after that in, I think, 2001, funded by the federal government to make sure that these people who were exposed to Libby amphibole got the health care that they needed. This is just a graphic. This is not data. This is something that I've used for a long time with my students just to get them thinking about outcomes, asbestos-related disease, or ARD. If we look at Libby, Montana, and all of the people who get sick there, I would ask my students, which of these diseases do you think is the most common in Libby? And they, of course, talk about asbestosis and mesothelioma because we think of those being so important in terms of asbestos exposure. However, if you look at it, we find that asbestosis and mesothelioma are actually relatively rare in Libby in terms of health outcomes. They're definitely higher in frequency than in many other places in the country, but they're not the predominant disease. Instead, these pleural diseases and autoimmune diseases and other cancers are predominant. most of asbestos risk is still determined by cancer outcomes, and yet they are not the predominant outcomes with amphibole exposure. So I'm going to talk about the pleural disease and the autoimmune disease a little bit and talk about the mechanisms that drive those. This is Libby's lamellar pleural thickening, and it is now being discovered as it's been published and people know to look for it. It's been discovered in several other places where the Libby amphibole was shipped and processed. So we know that it is occurring in other places. If you look at the black arrows on this CT scan, you can see that thin layer right inside the ribs, between the ribs and the lung. That's that thickening. And we're now working with researchers at Cornell University to come up with a way to quantify that type of fibrosis. This is by far the most common asbestos-related disease in Libby. The new EPA reference concentration for Libby amphibole is based on this disease, not on cancer. It's the first non-cancer outcome to be used in a regulatory manner. The disease is usually progressive, often fatal, and very painful, often requiring narcotic treatment. Patients essentially suffocate, and a lot of research on this has shown that it is sort of a combination of restrictive, of course, plus obstructive respiratory indicators. Outside of Libby, through sort of anecdotal information, it seems that this disease is being misdiagnosed as COPD or even simply as obesity with pleural fat. So my next slide is a study that was done a few years ago with the Card Clinic, but also with Dr. Ron Dodson, who's an expert in tissue burden studies. And so this individual had a lung carcinoma, and the surgeon was going in to work on that and agreed to let them photograph when they opened the lung or opened up the chest cavity. And so what you can see in this picture here is the lung, and this is the left parietal pleura showing that pearly white scar tissue. It was not fat, it was very dense, very difficult to cut through. And when they took out a piece of that tissue there and looked at it under the microscope, you can see all the asbestos fibers in there and some ferruginous or asbestos bodies. So there was no question that this was a fibrotic process driven by those asbestos fibers. We now have evidence that part of that process, this is a very progressive disease, it expands and grows through the lung, and our evidence suggests that there are autoantibodies that bind to the mesothelial cells that line the pleural cavity and change their phenotype into a collagen-producing phenotype. And because it is autoimmune, it just goes and goes and goes and goes and goes until the person can't breathe. Because of that, we believe that this is, at least in part, an autoimmune disease. The evidence for that came from the Libby screening population. We continue to screen as many people as we can coming through the clinic for these autoantibodies. The first one on the left are anti-nuclear autoantibodies, which are used for the diagnosis of autoimmune diseases, particularly systemic autoimmune diseases. And the autoantibody on the right are mesothelial cell autoantibodies that I show you in the previous picture. These antibodies that are actually binding to mesothelial cells and changing their behavior. In both cases, both of these graphs, we stratified the patients by their clinical severity and the progression of their disease. If we were seeing significant progression in the CT scans and in their symptomatic profiles over time. And we defined the rapid progressors as progressors, people that had evidence of disease but not progressing as stable, and then people with no disease are in the green bars here and here. All of these people were exposed, so there's no question about exposure. So the question was simply, is there an autoimmune component to this? And in both females and males, the ANA testing was very well associated with the progressor phenotype, and also the mesothelial cells autoantibodies were associated with the progressor phenotype. The Clark Clinic now is screening regularly. Everybody that comes into the clinic is given an ANA test and a mesothelial cell autoantibody test so that we have all of the data that we need. And we also use it to help patients discuss the potential for a progression of their disease based on their autoantibody test results. This is the ANA test that we used when I first went to Libby in 2001 and started screening people. We use this as a marker for systemic autoimmune diseases. And we published in 2018, I think it was, with Roger Deagle, who's a rheumatologist in Kalispell, Montana, who worked with us. And we've found that levels, prevalence of systemic lupus, systemic sclerosis, and rheumatoid arthritis are very high in Libby, sometimes 10 times as high as the expected prevalence in the United States. We also see significant amounts of sarcoidosis. As we were doing all of this screening, and I was working in my laboratory with my little tiny black patients that have long black tails, we found that although Libby Amphibole increased the percent of the animals that developed anti-nuclear autoantibodies, chrysotile did not. And so we came back to the table and said, well, can we show this in humans? So we needed to find a population of people who were exposed primarily to chrysotile. So we were given a set of samples from the Mount Sinai collection of samples from the steam fitters and pipe insulators who were exposed primarily to chrysotile. And we found again that while Libby Amphibole drives tremendous production of positive anti-nuclear antibody tests, the chrysotile exposed people did not. And finally, to put all of that together into a great big paper we published last year, this is our big review paper in Autoimmunity Reviews. What this is a table of all of the odds ratios for the development of positive ANA tests and the 95% confidence interval for as many papers as we could find in the historical literature where they tested anti-nuclear autoantibodies in people exposed to asbestos. The take-home point here is that if you looked at the exposures that were mixed chrysotile and amphibole and all of the different amphiboles, including fluoroedenite, have very high odds ratios for the risk of developing ANA, but chrysotile does not. I took out two of these over to the right. One of them was done in Australia, looking at the rate of ANA positivity among crucidolite miners and the people who lived in the town of Whitnum, where the mine was, against the Busselton study, which in Australia sort of equates to the NHANES study that was done in the United States to give screening levels for expected prevalences across the country. And so you can see that compared to the Busselton normals, if you could say that, Whitnum crucidolite exposed people developed very high frequencies of ANAs. And then the other study down below was in Italy. This was with fluoroedenite, which is a non-regulated amphibole, fibrous amphibole that it was used a lot commercially in Italy. And you can see that, again, that type of amphibole causes ANA. Let's look for a moment at silica. Crystalline silica is a well-known autoimmune trigger. Colleague of mine, Fred Miller, who has worked for a long time with the National Institutes of Environmental Health Sciences, said that silica is one of the strongest known risk factors for the development of lupus. And then in 2022, a group led by Jansen et al. Had a meta-analysis where they looked at all the rodent studies that looked at asbestos or silica. And their conclusion was that while both amphibole asbestos and crystalline silica can drive lupus-like disease in mice, amphibole asbestos was able to evoke the responses in healthy, non-autoimmune prone mice, whereas silica was not, making the evidence for amphibole asbestos slightly stronger in mice than for silica. And finally, last year in our meta-analysis, we were able to show that amphibole asbestos matched or exceeded silica in terms of epidemiology, mouse studies, and mechanistic support in terms of the mechanisms driving that disease. And yet, if you read papers today on autoimmune disease, you will read about silica being a trigger, but you will not, unless you're reading my papers, you will not read about amphibole asbestos being a trigger. And that's why we wanted to put out that big review paper to try to get it out there that indeed asbestos is, particularly amphibole asbestos, is a trigger for autoimmune disease. This is the picture that's in our big review paper from last year, looking at the mechanisms that drive that autoimmune. And if you overlaid silica on top of this, it would be virtually identical. We have various receptors, scavenger receptors and toll-like receptors that are able to be triggered by amphibole asbestos in tissue cells and macrophages. We have oxidative stress, cell death, and then loss of macrophages, so you have the inability to pick up and get rid of all of that dead cell debris. That makes this dead cell debris available for antigen presentation to the T cells, driving the production of B cell production of autoantibodies to that self-antigen, but also some signaling that leads to the blockage of the regulatory T cells that normally try to regulate these out of control autoimmune responses. A whole lot of things like inflammasome activation, chronic production of cytokines and immune recruitment, all of these things contribute to the chronic inflammatory situation that drives that autoimmune response. I want to talk for a moment about the term clearance. Clearance from the lung does not mean clearance from the body. So just because someone says that the fibers are cleared from the lung does not mean they're not still in the body causing damage. The only fibers that are really cleared from the body are those caught in the upper airways and the mucus of the trachea. I've got I don't know if you can see my sneezy picture here. There you go. Where you can cough it out, sneeze it out, or swallow into the GI tract, where most of the fibers are then lost from the body. But due to the very low Stokes number of the asbestos fibers that stay in the laminar flow of the airways, a vast number of these fibers travel deep into the lung, past the mucociliary escalator, where they could be cleared out of the body. And therefore, these fibers are not cleared. They may be translocated, however, via the lymphatics. So this is the lung lymphatics. This is a drawing by Netter, very, very detailed drawings and anatomical drawings. The green is all the lymphatic flow, and these are the lymph nodes through which that lymph will travel. And then if you take a little cutout here of this vast network of little tiny lymph vessels, you'll see that they totally surround each of the alveoli. And then there are tiny ducts that allow flow into the pleural space and then allow lymphatic flow between the pleural region and the diaphragm leading into the peritoneal cavity. So tremendous amount of flow and the potential to leave the lung and get to other spaces. Getting into the lymphatic system from the lung is very easy if you're small enough. Dr. Dodson, who I mentioned before, who does a lot of tissue burden studies, has found that the average length of fibers in the pleural cavity is about 2.5 microns. These are fibers that would not be detected if someone was trying to count them for exposure analysis because they're not regulated. Remember your physics that all fluid movement in the body is driven by changing pressures, delta P, and Ohm's law showing that the flow of the fluid is dependent on a flow change. And I bring that up simply because inflammation can change those pressure dynamics. So we may have our normal flow going from the lung back to the blood through the subclavian veins, but in inflammation, some of those directions change. And so that's really important for driving the asbestos to other sites, for example, into the pleural cavity. This is an interesting picture. I love this picture. It was drawn by an undergraduate student for an article that my colleague and I wrote last year for an open access publication. And I love this picture because of its simplicity, showing the fibers getting into the pleural space and then being able to get into the systemic lymphatics. Her picture shows free fibers being able to make that move, and we know that that does happen. But also they could be carried by macrophages. I put this picture in here. This is from my laboratory with mouse macrophages, whose diameter is around maybe 15 microns in diameter. And so you can, if you look closely, you can see that a bunch of these cells are jam-packed with tiny, tiny, tiny asbestos fibers. And so those could be picked up and then translocated into the lymphatics in the same way. This was a meta-analysis of the historical literature of tissue burden studies in 2023. And I'll just give you these quotations about their conclusions from that study. It was shown that asbestos fibers could translocate to the retroperitoneal and mesenteric lymph nodes besides their accumulation in lung tissue. So we see the lungs here. As we inhale the asbestos, it can get to the pleural space. It can get to the pulmonary capillaries. Once it gets in the blood, it can get pretty much anywhere. It can be into the lymphatics and get into the peritoneum. They also said that even low-level occupational exposures resulted in either chrysotile or amphiboles in the abdominal lymph nodes, and up to tens of millions of fibers of per gram of dry tissue were found in all of the tissues studied. And the take-home point really was that the vast majority of those fibers were less than 5 microns long, which would not have been detected as asbestos by current counting methods. Some of the fibers were larger in the GI tract. They were likely swallowed rather than being transported by the lymphatics. Why do we care about tiny fibers outside of the lung? We care about tiny fibers outside of the lung for one reason, is that they make up a large proportion of the exposures from commercial products and therefore occupational exposures. So this study was done in 2014, and it's been followed up since then, showing that the short asbestos fibers, meaning fibers less than 5 microns long, are these lavender bars. Up to 96% of the product, the asbestos released from those products are the tiny, tiny fibers. These are the World Health Organization fibers that are actually regulated, but they're a minimum smaller frequency in these commercial products. The second reason we care about tiny fibers outside of the lung is because that's what the immune system is going to deal with. Asbestos-caused cancers occur outside the lungs, and the fibers that arrive there are very, very tiny. No studies to date evaluate fiber length when looking at autoimmune disease, although we have that work in progress. This is my simple schematic and your little review of the immune system this morning, showing the antigen presenting cell being able to present exogenous antigens that have been taken in to the phagolysosome and presented to T cells on MHC. And then we have endogenous antigens like viruses or cancer antigens that can be presented. Depending on the MHC that's being used and presenting to the T cell, we end up either with a T cell cytotoxic response, which can go back and kill the cancer cell or the virus-infected cell, or we get a T helper cell response, which helps to drive the B cell production of antibodies that will go after these exogenous antigens. While I'm sitting here on this page talking about beryllium, I mentioned that at the beginning. What beryllium does is actually bind to the MHC molecule and cause presentation of endogenous antigens as foreign. And so as this interaction occurs, the T cell sees it because it's been altered by the beryllium to look like a hapten. A hapten is a modified self-antigen. The cell sees that as foreign and develops a whopping big CD4 response, and so you get those T cell granulomas. While the antigen presenting cell is doing all this presenting of the antigen to the immune system, it's also producing different inflammatory cytokines, damage-associated molecular patterns, which are sort of like adjuvants. to excite the immune system, and then reactive oxygen species in their attempt to kill the microbes. Unfortunately, asbestos cannot be broken down in the phagolysosome. So what you end up with here, as after they take in those fibers, is damage to the phagolysosome, which really activates tremendous inflammatory responses. This is my graphic showing the sort of simple division of labor, so to speak, of the immune system. If it's a virus-infected cell or a cancer, the immune system has to go back and kill that cell. So you drive this Th1 response and those cytotoxic T cells to go back and kill the cancer cell or the virus-infected cell. If you have external pathogens like bacteria or toxins, you want a Th2 response, which is going to activate the B cells and make your antibodies. This response also goes to the IL-10 resolving and healing response with a tissue healing, and then also the Th1 response should resolve and go to the IL-10 wound healing response. If the antigen-presenting cells are getting mixed messages or confused messages or damage to the macrophage, they send out a whole collection of cytokines that drive what's called a Th17 response, which is an unresolving inflammation, and it's seen with cancer and autoimmune disease. So when we treated our macrophages and are in the presence of the immune system, Amphibol drove this type of response. We get a big Th17 response with a huge amount of IL-17 and this unresolving inflammation. With chrysotile, interestingly, we don't get that. We get a tremendous reduction in all of these cytokines, and then we get a lot of IL-10, which is actually immunosuppressive. I'm not the only laboratory that's shown this. There's a group in Japan that's been working on this, Takemi Atsuki, who's been showing that chrysotile is immunosuppressive for a very long time. And when you have in something that's suppressing the immune system, especially if you're not getting your good anti-cancer response, that makes the body more susceptible to cancer. Both asbestos and silica have been shown to bind to a whole big family of different receptors that bind patterns like polyanions and zwitterionic surfaces. And also, both of these have been shown to actually bind directly to the T cell receptor, activating T cells without any regulation on that T cell. All of this results in mixed signals for the cells, depending on the cell type and their specific signaling capabilities, so that you get a whole lot of things happening in the cell that the cell really doesn't know what to do with those fibers. And so most of the time what happens is some kind of cell death. And if you follow the literature at all, you know that they keep coming up with new forms of cell death. We started out, when I started in biochemistry, there was apoptosis and there was necrosis. Well, now we have necroptosis and pyroptosis. Whatever all of those are, some of them pro-inflammatory and some of them anti-inflammatory, asbestos has been shown to induce all types of cell death, depending on the tissue type, the cell type, and other conditions present. Just to show you that apoptosis is not always protective, this study that we did years ago shows that asbestos can cause altered self, meaning the immune system is going to see self proteins as foreign and therefore will mount an attack against it as an autoimmune response. We use mouse macrophages stained red for the nucleus, green for the autoantigen RO52, which is a ubiquitin ligase, so predominant in all cells. And then we have this pink is the membrane of the cells. After treatment with Libby Amphibol, we see the cells undergoing apoptosis with creation of these apoptotic blebs and bodies, disintegration of the nucleus, and that RO52 is clustered in these apoptotic blebs. And what we find is that RO52 is now modified to look foreign to the immune system. And we know that because if we take the autoantibodies from the mice, they actually bind directly, that's the red stain here, those antibodies actually bind to and recognize these apoptotic blebs and bodies as foreign, driving an autoimmune response. This was a study done by Lenardi in 2023, where he tried to tease apart some of the things going on with macrophages trying to deal with asbestos fibers. So he had a preparation of primarily short fibers, and then that was primarily long fibers. It's impossible to get a pure sample of just all small fibers or large fibers. We haven't figured out how to do that yet. NIH is working on it, so we're waiting for them to come up with a really cool method. But what Lenardi found was that tiny, tiny fibers can bind to a single receptor and be internalized. And what goes wrong with this situation, if it gets internalized, is that the phagolysosome cannot break it down. It's a mineral, so it just stays there, and it ends up damaging the phagolysosome, and this activates the NALP3 inflammasome and can trigger huge amounts of inflammation and eventual cell death. What he found was that the longer fibers can actually cross-link multiple receptors, leading to a lot of confusion in the cell and different forms of cell death after that, with tremendous production of reactive oxygen species and tumor necrosis factor. So we're not to any degree at a point where we can determine exactly what long and short fibers do, but there is work going on right now to really take a look at that and determine the contribution of the long and short fibers to the health outcome. Very quickly, I want to mention the oxidative stress. The production of ROS is very common within cells, but it only becomes oxidative stress when our ability to scavenge the ROS is compromised. And one of the main scavengers is glutathione. Cellular responses to reactive oxygen species are another way that the immune system can be altered, and I want to mention two of those. One is redox signaling. The redox signaling has been shown to polarize immune responses. The other one is lipid peroxidation, and that is the production of lipoxins and resolvins. I don't know if you've heard of these, but these are lipid mediators that actually help to resolve inflammation. I have a colleague right now who's working with Libby MT. This is Kinta Survey at Idaho State University, is working with Libby MT and other fibers to determine what drives the production or prevents the production of these wonderful resolving lipids. This is the redox signaling idea, where you can change the immune system's response by plugging in these little transporters right here. This is system XC, and it's an exchanger for glutamate and cysteine. So it brings cysteine in order for the cell to make glutathione for dealing with oxidative stress, but it kicks out glutamate. And if you know anything about glutamate, you know it's a signaling molecule. The nervous system uses it all the time, but so does the immune system. T cells have glutamate receptors on them. So the cell being in oxidative stress becomes a signal. What we showed was that Libby amphibole, crucidolite, another amphibole, and lipopolysaccharide all drive the expression of this little transporter, but silicus does not. So an interesting difference between two exposures that cause reactive oxygen species, but a difference in how the cells deal with it. This was a work done by Morris in 2022 looking at redox regulation of immune responses, and his simple, I have simplified his conclusions, showing that the glutamate goes to the T cells, and if there's just a little bit of inflammation, you can get this Th1 response. If there's a lot of oxidative stress in inflammatory cytokines, it drives a Th17 response. And then if there's way too much oxidative stress to overcome the ability of the system to deal with the reactive oxygen species, glutathione drops to the point where the cell dies. So this is redox regulation of the immune response. Here is my final slide. It was my attempt last night, very late, trying to put this all together into a picture, talking about the different things I've mentioned: particle size, receptor signaling, types of cell death, and the immune effect. and then looking at the different exposures I've been talking about here. And then I tried to use color blending to show that the long fibers in beryllium stay mostly in the lung. They're bind to receptors but are not internalized. They drive chronic tissue damage. And then beryllium itself drives hapten-mediated T cell activation and recruitment and T cell granulomas, whereas the long fibers induce DNA damage, plus foreign body responses and a non-resolving Th2 inflammation. And all of this then can drive interstitial fibrosis. All of the exposures cause ROS and DNA damage, but the ROS effect may be different with the different types of exposures, as we saw with silica compared to Libby MT. The short fibers are translocated to the pleural and the pleura and the lymphatics. They're internalized, but they can't be processed because they're mineral, so you lead to all kinds of inflammatory processes that alter the antigens, and you get an altered immune response that's driven by Th17 cytokines. This leads to a poor anti-cancer response, and we see that with both long and short fibers, so I made that purple. And so you end up with cancer. You also end up with some pleural fibrosis with these fibers that are translocated to the pleura, and mesothelioma. And finally, I think it's probably a combination of short and long fibers, but with the short fibers really driving the autoimmune disease process. I hope that's helpful. Obviously, I have not answered the question about how all these occupational exposures can cause disease, but I hope I've given you an idea of where we can go to look for some answers. I will finish with this one. This is in the top of the slide here. It has the graphic. This is a Calgary guide from the University of Calgary on pneumoconiosis. And it is wonderful. I was so excited to find it because here's asbestosis, silicosis, metalloconiosis, and carboconiosis, all driving some of the very things that I've talked about today, but focused on the health outcome that you're going to see in the clinic: cough, pulmonary hypertension, dyspnea, etc. And it's just fantastic. And so maybe I should have just shown this slide and we'd have been done today. Thank you so much for your time.